Hello, everyone. Today we'll be continuing our discussion about the binomial distribution. Particularly, we'll be talking about um, how to find the expected value, how to find the variance, and the importance in finding the expected value and variance because we're going to be finding a normal approximation to the binomial distribution. So we have to talk about what that means as well. Um, yeah, and then we'll be talking about this last thing called sample proportion, and then we're done. So let's first do this question. I toss a fair coin 6 times. What is the probability I land on heads at least 3 times? Okay, so if we make x the random variable and it's modeled by a binomial. Now I know it's a binomial because there's only 2 options, either heads or tails, and they have complementary probabilities. N is the number of times I'm tossing the coin, which is 6. And the probability of a success in each Bernoulli trial or in each trial is a half, because probability that I land on heads is a half. Nice. Right now, what's it saying? I want to find the probability that x, which represents the number of heads I land on, to be at least 3, which is greater than or equal to 3. Okay. So this is quite easy, nothing new for this. We just have to give our cases. Now, there's 2 ways you can do this question. The first is you can say that it equals probability that x equals 3 plus probability that x equals 4 plus probability that x equals 5 plus probability that x equals 6. Okay, I'm kind of Siebes, so I'm not going to do this one. Instead, I'm just going to do a complementary. Okay, and the complementary says 1 minus the probability that x is less than 3. Now, because you only have integer values, you're only going to say 1 minus and then the probability x equals 2 plus probability x equals 1, and make sure that you also have another case x equals 0. So I'm going to do this second one. But how are you going to do each of these? How are you going to compute the probabilities? Well, we have to go back to our binomial distribution, and we recognize that the probability that x equals, we'll say little k, is given by n choose k, and then it's p to the power of k, 1 minus p to the power of n minus k. And that's, of course, if x follows a binomial np. So in this case, we follow the binomial 6, 12. So probability that x equals 2 means that we're going to say 6 choose 2. And then so a half to the power of 2, and then a half, which is 1 minus a half, but that's the same thing anyway. And then that's going to be to the power of 6 minus 2, which is 4. And then minus, and then this is 6 choose 1, a half to the power of 1, then a half to the power of 5, and then minus 6 choose 0, a half to the power of 0, then a half to the power of 6. Anyway, we can just sort of simplify this. Because there's a half to the 6 in each of these, if you just, I guess, clean up the powers or use index laws, 1 on 2 to the 6. And then what's 6 choose 2 plus 6 choose 1, 6 plus 6 choose 0 is 1. So 22. There you go. And then 1 minus 22 on 2 to the 6. Oh, okay. Not bad. 21 over 32. So the probability that we'll have at least 3 is 21 over 32. Fair enough. Okay. I don't see anything wrong with the question like this at all. We sort of get into issues when we have a question like this. I toss a fair coin 100 times. What is the probability that I land on heads at most 33 times? Okay, so this is a pretty annoying binomial. Because the binomial for this question is x equals, or x is a binomial with number of trials 100, and with probability of success in each trial being a half. But if I want to find probability that I have at most 33 heads, that's this. Okay, now this is a bit of an issue because if you want to find this, you actually got to do all of the cases. You got to say x equals 0, x equals 1, x equals 2, x equals all the way up to 33, or you say 1 minus the probability that x is greater than 33. But then in that case, you're stuck with even more cases. So we definitely have to be able to come to we have to be able to approximate what this value is. Now, granted, I guess the way your calculators work or the way your software works, if you're ever going to do this in the future, you're never actually going to be using this approximation. At least I don't think they do. But I know by hand we use this approximation. Yeah, a lot of times you want it to be very, very accurate, especially if you're doing stuff like hypothesis testing, which is something that you might do in the future. In that case, I know I don't really use this approximation. But anyway, whatever. Alrighty. So before we sort of move into the approximation, we just need to talk about two things. Actually, no, let me just mention something about the approximation. We're basically going to find a way to approximate the binomial distribution with a normal distribution. So we're going to take this discrete random variable, because binomials are discrete random variables, and we're going to approximate it to make it continuous. Okay. But if we're going to do that, we first need to talk about the mean and the variance of a binomial distribution. So this is just something that I have to, I guess, just tell you. Okay. Unfortunately, it's not super necessary for us to go through how to find the expected value and the variance. So I'll just chuck it in. So the expected value and variance for binomials. Okay, so if x is a binomial with parameters n and p, the expected value of x equals np, and the variance of x equals npq, but you'll probably have it written as np1 minus p. So q is just the complementary probability. Okay, maybe the second one doesn't make that much sense, but the first one does, I think. Like the expected value, what you sort of expect to happen is just the p, which is a probability of a success multiplied by the number of trials you have. Okay, I think if I give you an example, it may make a bit more sense. So let me just chuck this in. I roll a dice 120 times. How many times do I expect to see a 6? Well, okay, you don't even have to have done year 11 and 12 probability to maybe suggest to me an answer. Okay, I know that this is sort of explained a bit early on, maybe in like year 8 and 9. And you could probably ask it and it just makes sense, doesn't it? Like if I roll it 120 times and each side is equally likely with probability a sixth, how many times do I expect to see a sixth? Well, that's kind of like asking what's the expected value or what's the average. Well, on average, I expect to see it a sixth of the time. So what's 1/6 of 120? And you say, that's 20. So you'd expect to see it 20 times. Of course, that's probably not what's going to happen. However, that's just the expectation. Fair enough? Nice. So now let's talk about the normal approximation to the binomial distribution. So now that we've discussed how to be able to calculate the expected value, how to calculate the variance, we can now talk about the normal approximation. So let's chuck this in. Okay, this is pretty important. Okay. And I'll chuck in an interesting diagram. So this here is a screenshot of one of my lecture slides. And I really didn't want to recreate these diagrams myself. So I'm just going to take their sliders instead. So what you can tell, they've sort of created these little histograms or bar graphs that represent the probabilities of landing on particular values for different binomial distributions. So this here, this first binomial, 501, what that says is that there's 5 trials or 5 independent trials. The probability of success in each trial is 0.1. And these blue bars here represent the probabilities of landing on of getting 0, getting 1, getting 2, getting 3, 4, and 5. Doesn't really look like a normal distribution, does it? But what you can tell is, as you start to increase the number of trials, so you go from 5 to 10, then from 10 to 30, then from 30 to 200, keeping the same probabilities, you start to see that these bars start to sort of look like the normal distribution, don't they? Maybe not this one as much, but still, it's reasonable. This one a lot more, and then this one very much so. So because we can start to tell that the normal distribution becomes a good approximation to a binomial distribution when you have a high sample space, or when you have a large number of trials, then for harder questions, ones where you have to give many cases, like this one, you're doing 100 trials over here, it becomes very good at approximating these sorts of inequalities. We may be able to convert them into with Z scores. And once we find Z scores, we then go and I guess go to the Z score table and find those values. But anyway, that's the idea. So yes, this becomes very useful. So how can we write this? Oh, and we also have a little point to make. Actually, let me just make my point here. Now you might say, well, we've kind of just given this example and we've increased the samples, the number of trials from 5, 10, 30 to 200. But how are we supposed to know what number is like the turning point? I think what's sort of agreed upon is that if NP is greater than 5 and N times 1 minus P is greater than 5, then X, which is a binomial, and P will effectively start to become some new variable, we'll call it X, which is normal, and it has mean. What did we say the mean was? NP. And what did we say the variance was? NP 1 minus P. Okay, so that's generally the idea. If N times P is greater than 5 and N times 1 minus P is greater than 5, then we can use our normal approximation to the binomial distribution. Lovely. Okay, this is very important because remember how we spoke about standardizing normal distributions? Well, that's what we'll have to do. Always keep this question in mind because we're just about to start answering it. Obviously, this particular case doesn't have a mean of 0 and a standard deviation of 1. So we'll have to find the mean and the standard deviation. Then we'll have to find the Z-score using that Z equals X minus mu over sigma equation. And then we'll have to go to our Z-score table and find the respective value. Okay. But we also run into another issue that I have to mention. It's called the continuity correction. So think about the fact that we're going from a discrete random variable to a continuous random variable. We're going to run into some issues as we sort of make this approximation. Sometimes we'll be assuming certain things that don't actually make sense, and therefore we have to make different corrections, or such that we can account for those little assumptions. So, of course, a discrete random variable, let's say it's the tossing the heads or whatever, tossing the coins, and see if we land on heads. You can't get in between values. Like you can't have a 33.5, or you can't have a 22.5. But we may need to use those values to be able to approximate it better. So let's say this is, this is X, and these are all of the outcomes that we can have, and 0 and 100. Now the peak is at 50. So I kind of want to, damn, this is kind of tedious, isn't it? Okay. Now this is our histogram, and it represents, say, landing on 50, and then 51, 52, 53, 55, and then 49, 48, 47, 46, 45. And then, of course, that goes on, and that goes on that way as well. So what we're saying is this discrete random variable starts to actually look like a binomial, or sorry, it looks like a normal distribution. Okay. If I ask, what's the probability that X is less than or equal to 47? Can I just draw a line here at 47, some vertical line, and say, I'm going to just take everything to the left of this? Not really. The reason why is because if we look at this histogram, if I we'll actually be under approximating the probability. Now, there are kind of more hefty and mathematical reasonings for why that's the case. The reason that I sort of justify for myself whenever I have to do these questions is, yeah, this is kind of dodge, but see how this is a full bar or a full, rectangle? By taking exactly at 47, which is the center of this bar, you're missing out on half of the 47, because of course we have to take all the way. Oh no, there we go. We would have to take all the way from here. Okay. That way we can get the full 47 bar into it. Okay. And that's because if you don't have 47, you have to hop directly to 48. And therefore we sort of take the middle between the 47 and 48. Okay. That's sort of the justification. So what the continuity correction does is, it says, well, when you're approximating a binomial to a normal, always ensure you are including the full bar in that histogram. That means instead of saying X is less than or equal to 33, and then using that, 47, and using that, because we want to include the entire 47 bar, that is all of this, and then all of this, and all of this, we actually have to go a bit more to the right and say, no, that's better to be saying X is less than or equal to 47.5. Okay, perfect. What about if you wanted to say the probability that X is greater than or equal to 51? Okay. You couldn't, just like before, draw a line at 51 and say, that's how I'm going to do it. Because you want to include the entire 51, you will have to say, you have to minus a half from this. because of course this has like length of 1. So you got to take a half of it and go back. So you would say, actually, no, this is better to write as x is greater than or equal to, and then 50.5. Does it really matter that I have it less than or equals or greater than or equals, like the or equals part? Not really, because in continuous functions or continuous distributions, it doesn't actually matter if it's an or equals. Perfect. What if you say probability x is less than 47? We'll do 46 just so that we don't sort of get confused. Okay. If you say x is less than 47 or 46, let's go to here and chuck in our 46. If you just say x is less than 46 and you use that to approximate using a continuous distribution, you actually be including part of the 46. So instead, you got to move a half to the left so you can go straight to the 45. So that you can only include the 45 and anything to the left. And in that case, you would have to minus a half and go to 45.5. So do you see how it really does depend on the structuring of the question as to whether you add/subtract? I hope it does. Nice. Because you can see last time I added, but here I subtracted. Okay. And I'll give one more. It's a probability that x is greater than 53. Okay. If x is greater than 53, I hope you can tell that we should be adding 1 and saying 53.5 so we can get to there. Nice. And then what you do is when you go to actually approximate it using the normal distribution and you find your z-scores, you would use this score, this score, this score, and whoopsie, this score. Nice. So let us do this question here. Actually, let's do that question from before. I toss a fair coin 100 times. What is the probability I land on heads? At most 33 times. So here I want the probability that x is less than or equal to 33. Well, what I have to do is I have to change this and make it probability that x is less than or equal to 33.5. That way I'm including the full 33 bar from the histogram. Okay. Now, if I'm going to use my z equals x minus mu over sigma, I have to find what the mu and the sigma are. So mu is mean, that's given by NP. So it's given by 100 times a half, which is 50. Now, sigma is given by 100 times a half times 1 minus a half, which is a half as well. And that's going to give you 25. And sorry, the square root of that, because the inside's variance, which is 5. So now, when I'm trying to find my z-score, I'm going to say 33.5 minus the mean, which is 50, over the standard deviation, which is 5. There we go. So now we're going to say this probability that we're trying to calculate is approximately, so we'll say probability x is less than or equal to 33, is approximately the same as saying the probability that z, which is our normal distribution, is less than minus 3.3. Because that's our z-score that we calculated. Okay, of course, this is the same as saying phi of minus 3.3. We don't have phi values for negatives. So this is the same as saying 1 minus phi of 3.3. And then go back to the table that's in one of our booklets, or it's in one of the other videos as well, slash just Google it. I'm going to find 5 3.3, and that is, there we go. One minus 0.99952. Okay, and I didn't even need a calculator for that. What am I doing? So this is 0.048%. You might say that's quite low, but I guess it is, considering that like most of them are going to be around the 50. So if they're saying less than 33, it's going to be very, very small. I mean, if you have a, like, I guess none of you have really maybe thrown coins that much, but I cannot imagine tossing a coin and 100 times and getting 33 or less heads. Like that probably suggests that maybe my coin isn't, um, you know, isn't, what's it called? What am I saying? Isn't a fair coin. Yeah. In fact, that's something that you might do in university called hypothesis testing, which I think is pretty cool. Okay, anyway, let's do another question. I'll let you have a go at this. Again, this is a process. Find the mean, find the variance, find the Z score, do your little continuity correction, and bada bing, bada boo. So how about this? Have a go, pause, and then unpause. So a coin is tossed 20 times and X is the number of heads. Find the probability that the number of heads is greater than 12. So using a binomial distribution, and then B, using a normal approximation. So part A, saying using a binomial distribution, means give me all the cases. That is, the probability that X is greater than 12 means that you're going to have to be saying probability that X equals 13 plus probability X equals 14 plus all the way probability X equals 20. Now I am definitely not bother doing this. Okay, so yeah, unfortunately I'm not writing that out. Part B, using the normal approximation. Okay, so first of all, probability X is greater than 12. We have to account for our continuity correction. Think about it in terms of the boxes. You want to go after that box or after that rectangle. And this is then going to be actually probability X is greater than 12.5. Now I'm very aware that I'm probably maybe putting equal sign, less than or equals, or greater than or equals, maybe where I shouldn't. In this case, I think it's fine. But remember, with continuous approximations or within any continuous distribution, the all equals doesn't matter. So that's why I'm pretty casual about it. Maybe I shouldn't be, but yeah. Okay, so we want probability X is greater than 12.5. Now, of course, we need to find the Z score, which means we need to find the mean and the variance. So the mean is given by NP, so 20 times a half, which is 10. And then the variance is given, and then, sorry, this is standard deviation. Standard deviation is given by the square root of the variance, and the variance is given by NPQ. So N 20 times a half, which is given as the square root of 5. So here, this is actually going to equal the same thing as the probability that Z is greater than 12 point, can you hear those birds? No, 12.5 minus 10 over root 5, which is like the respective Z score that I haven't calculated yet. What is the Z score? 12.5 minus 10 over root 5, 1.118. 1.118. Nice. Now, I think that table only goes to 2 decimal places. So this is the same, we'll say, as probability that z is greater than 1.12. Now, of course, we don't have for greater than. All of our z-score tables are for less than because they're the cumulative. So this is the same as saying 1 minus that. And 1 minus 5, 1.12 is, where is 1.12? 0.86864. 86864. Okay, nice. 1 minus 0.86864. Okay. And let's see. Maybe that's the correct thing. 0.13136. Nice. 13.136%. There you go. That's that one. Yeah, that's how you sort of do these normal approximation questions. I guess I'll give you another one. Okay, a coin is tossed 20 times and X is the number of heads. Find the probability that the number of heads is within 1 standard deviation of the mean using a binomial distribution and then using the normal approximation. Comment on the results of the calculations. You can have a go on your own. You can just wait for me to do it. I mean, I'm not going to know. But let's write out our binomial. But all of these are tossing coins. Okay. Binomial. 20 a half. We already did this. We found the mean to be 10. And we found the standard deviation to be the square root of 5. Okay. So, A, what's the probability that X lies within 1 standard deviation of the mean? So it means X is, well, the mean is 10. So 10 plus root 5, and then 10 minus root 5. That means you're within one of those root 5s from the 10. Perfect. Well, what actually are these values? 7.76. Maybe I didn't need to go into that much detail. 12.236. Alrighty, well, if X has to lie between these two values, for part A, what we can say is, well, actually not even just for part A, for both parts, so really this is not even, yeah, we can say that just means that we want the probability that between 12 and 8. Now, why am I doing or equals? Because if it has to be more than the 7.76, it can be 8. If it has to be less than the 12.236, it can be 12. Okay, so no continuity correction just yet. This is purely just normal binomial distribution. I could have asked this question even before we started talking about today's content. Now, actually, no, because you need to find the mean and the standard deviation. But besides that, no normal distribution stuff. So in part A, you would just do cases for this. You would say this is probably X equals 8, 9, 10, 11, and 12. And each of those have their own thingies. You would just figure it out. I think I've already written the answer to this, and it's approximately 0.737. Now, for part B, probability that this is the case, well, you have to use your continuity correction now. So your continuity correction is going to mean that instead of just saying X has to be between 8 and 12, you actually have to ensure you've included the entire 8 and the entire 12. And that means that you're going to say probability that is between 7.5 and 12.5. Okay, perfect. And now you have to figure this out. So you have to find out what the Z scores are. So when Z equals 7.5, I'm going to minus 10 and divide by that. And then this is going to equal minus 1.118, so minus 1.12. And then the other one, Z equals 12.5. Oh, wait, it's 110. They're going to be the same thing, aren't they? Yeah, mad. So now this here is the same as saying, why am I writing? Probability that Z is between 1.12 and minus 1.12. Again, using all of our rules that we've discussed beforehand, that's 5 1.12 minus, and then this is 5 minus 1.12, and then 5 1 minus is the same as 1 minus 5 the positive. So this becomes 2 of these 5s minus 1. And what did we get that? 2 times 1.12. We found this before, didn't we? 0.86864. 86864 minus 1. What do we get in part A? 0.737? 0.737, pretty good. So doing it case by case, using the approximation, it worked out quite well. I think if you want to prove to yourself that the continuity correction is necessary, then maybe this isn't the best case because the numbers are so small. Like you're not going to a Z-score table that has 3 decimal places. You're just going to 2 decimal places. So you probably won't tell that much of a difference. But there is a difference between not using a continuity correction and using continuity correction. Sometimes, though, it can be avoided, particularly if you have such a high number of trials. For example, if you're tossing 10,000 coins, then it's not going to matter that that you didn't, add 0.5 and minus 0.5, because adding 0.5 and minusing 0.5 to, like 4,000 is not going to make a difference. Okay. Now here is this other question. So puppy, it's not really, it's a binomial question, but it uses some binomial distribution properties. So approximate 100, choose 53 using the normal approximation to the binomial distribution with this distribution here. Check how good the approximation is. Okay, so I'll just show you how to do this question. It's saying we want to find a way to calculate what 100 choose 53 is, but we want to be able to use our normal distribution to calculate it. And the way we're going to use it is through this binomial of 100 trials and the probability of success being a half. So what I'm going to say is if there was this binomial with 100 and a half, then the probability that x equals 53 is going to equal 100 choose 53 times a half to the power of 53 times a half to the power of 47. Now that's going to be 100 choose 53 times 1 over 2 to the 100, because those ones add to 100 anyway. So we know this, but we just need to find a way to approximate this left-hand side. So to be, a good approximation is to say, let's actually make this between 53.5 and 52.5. That's kind of like getting the entire rectangle from your histogram, isn't it? Like the 53 is in the middle of the histogram. So you got to go half to the right and half to the right for you guys and half to the left so that you can include the entire box. Now for this, again, you can just find the z-scores for each of these. And once you've found the z-scores, you have to um, go to the z-score table, find out what this is, and then multiply it by 2 to the power of 100 to get the 100 choose 53. Okay. I think if there's any questions, just let me know. But yeah, that's that. Okay, and the last thing that we have to discuss in terms of statistics is sample proportions. So sample proportions concerns where we're not really worrying about the number of successes, we're more worried about the rate of successes or the proportion of successes. This is used all the time. Arguably, it's probably more relevant than the number of successes itself, particularly if you're trying to find like how many people in the population or the percentage of the population who favors a particular political candidate. Okay, that's kind of more important, or the rate of people getting into motor vehicle accidents, given that it was projected that this would be the rate. Okay, so this is useful because we have sample size. We don't use the entire population in a lot of our surveys because it's quite expensive. So when you have a smaller sample size, it's relevant to use sample proportions and be able to test how effective or how accurate those sample proportions are. Anyway, so a particular question that we could, this is an easy one that I wrote, is if I roll a dice 100 times, what is the probability I roll a 6 32% of the time? Okay, maybe 32% is not the best number, but the idea is that we're considering a rate. Okay, now sample proportions obviously can come from many different distributions. We're going to be particularly concerning ourselves with the sample proportions that come from a binomial distribution. So if X, this is an example we'll put here, if X is a binomial NP, then we call this thing the sample proportion, and we denote this by P with a little hat on top. Okay. Now this P hat is given as X over N. So let's give a particular example. If X represents the number of heads that you land on when you toss N number of coins, well, then the proportion is given by the number of heads that you land on divided by the total number of times you actually toss the coin. Okay. So it's the rate. Well, so it's directly related to the binomial distribution in this case. So because our sample distribution is going to have its own, our sample proportion is going to have its own distribution, really, we need to talk about its expected value. And we need to talk about its variance. So the expected value of P hat, well, P hat is given as X on N. So it's given as the expected value of X over N. Now, one of the rules that you have to know with this stuff, and it was in year 11, is that you can actually take that constant out. It's that 1 on N. You can take it out and it becomes the expected value of X. Now, we know what the expected value of X is in your from the binomial. You might be worth writing this in. Okay, so it's 1 on N times NP, which means the expected value is P. Okay. And then the variance is given as variance of X on N. Now you have to know that I can take the 1 on N out. However, because variance is the square of the units that we're dealing with, we'd actually have to take it out and make it 1 over N squared times var of X. And then this is 1 on N squared times NP 1 minus P, which is given as P 1 minus P over N. And there you go. That's how you calculate this. So you have to know these because I don't believe they're given on your reference sheet. Now they're pretty easy to derive, aren't they? I mean, no response, but they are pretty easy. You are expected to know these little rules where you can take it out and square it, or you can take it out like this. So make sure you know this. Very nice. So that's that, and that's that. Now let's continue on because we have to. I guess I can give you an example. Let's say okay, a binomial experiment with, let's say, 30 trials. Okay. Um, has actual value of p to be equal to a third. Okay, so what is the probability? P hat, which is the sample, is going to equal, and actually, let's try to make this a bit more interesting. 10%. Okay, so you can tell we're asking ourselves what's the probability for the binomial, the sample proportion rather. But our sample proportion is directly connected to our binomial distribution. Okay, like you can tell here that this binomial experiment, we can give it x. X is a binomial, and it has 30 trials, and then it has a probability of success being a third. Okay, if it's saying what is probability p hat equals 10%, well, how do we ever calculate p hat? We calculate p hat by taking the x, the number of, I guess, successes, and then dividing it by n, so dividing it by 30. So asking yourself, what's the probability that the sample proportion is 10% is the same as saying, is the same as solving this question, so timesing by 30, timesing by 30, and getting, well, this is just 3. So it's the same as asking us, what's the probability x equals 3? Because x equaling 3 gives you a sample proportion of 10%. So an easy question like this, you just ignore all of the extra buffer and say, well, if the sample proportion is 10% and you did the trial 30 times, that means that 3 of them must have been successes. So then you say, okay, well, what's the probability that you have 3 successes? Now you can just ignore the p hat. You've sort of dealt with it. You could say probability x equals 3 means out of the 30, you choose 3, and then it's a success 3 times and it's a failure the other 27 times. And you can find out what that value is. Okay. I hope that sort of makes sense. This isn't the type of question that we actually get, but you know, I hope that sort of explains part of it at least. Okay. Well, just like our binomial distribution being approximated to a normal distribution, our sample proportion can also be approximated to a normal distribution. So p hat can also be approximated to a normal distribution. Very nice. You just have to make sure you know the mean and the variance so that you can standardize it. That's really kind of it. Now, in terms of how we would actually calculate this, oh, okay, actually, before we get into that, there's a few points we have to make. First, are there any conditions? Like before I said NP has to be greater than 5 and NP and 1 minus p has to be greater than 5. The conditions here are a bit different. They're not mentioned in your textbook, but from my own understanding, they look something like, okay, hold on. Just gonna make sure I don't mess this up. I think the rules are if let's write this a bit differently, a bit better. Okay, so this is the point. It's if the mean minus 3 of the standard deviations, the interval from this to this is fully within 0 to 1, then it's approximately a normal, then you can use it. It's not really written in your textbook, so I guess I don't know. I don't know. It's up to you. But that's the rule. The second thing is, before we had a continuity correction. Do we need a continuity correction? You could, but it's not necessary. So continuity corrections are unnecessary. Okay? That's just fact. The reason is because we're already, like, even though X is a binomial distribution and it's discrete, the sample proportion is no longer really discrete, because like if you had 7, for example, in this case, like if X equaled 7, 7 over 30 is a recurring decimal, right? Like there's no, yeah. Actually, wait, that would still work. I don't know. Generally, we just don't do it because I think it's already an approximation where we don't care if it's a bit under approximated. So we just don't use any of the plus 0.5 minus 0.5. Okay. Now let's do a little question for you guys. So let me just try and find it. Okay. So proportion of a population with a characteristic of interest, whatever, is P equals 0.37. So the probability that whatever's happening is 0.37. Find the mean and standard deviation of the sample proportion P hat obtained from random samples of size 1600. So try not to look back at in the video to calculate what the expected value and the variance is, or it's a standard deviation, but try and just, knowing that P hat is X on N, try and derive what expected value would be and what the variance would be as well, and then therefore the standard deviation. Okay, once you've had a go, unpause. So expected value is given by expected value of P hat rather. It's given by expected value of X on N, which is 1 on N times the expected value of X. And then this is 1 on N times NP, which is P. So expected value of P hat is 0.37. And then the variance of P hat equals the variance of X on N, which is 1 on N squared times NP1 minus P, which is, and then 0.37 times 1 minus 0.37, which is 0.63 over N, which is 1600. Okay, this is 0.0001456875. And then we can say the standard deviation of P hat is equal to the square root of that answer, and 0.0121. Nice. There you go. What if a question said, suppose that 8% of all males suffer some form of color blindness. Find the probability that in a sample of 250 men, at least 10% will suffer some form of color blindness. First, verify the sample. Okay, we're going to stack off the second part because it's not going to be asked of us. Or you'd have to do the mean plus 3 of the standard deviations, and then minus 3 of the standard deviations, and plus the the thing that I wrote before. So we're trying to say, what's the probability that p hat is greater than, it says at least 10%, so greater than 10%. So because this is going to be approximately normal, we have to find the expected value of p hat, and we have to find the variance of the standard deviation of p hat. Every time you do this question, I want you to derive it so that you remember it. Okay. Well, the expected value of p hat is just going to equal p, which is, it says 8%. So that's going to be the actual value, 0.08. And then the standard deviation is going to equal the square root of, it was p1 minus p over n, all within it. So this is going to equal the square root of 0.08 times 0.92 over, how many people are we sampling? 250 over 250. Nice. I'm not writing out the entire thing, but I am going to be using the entire thing. Now, we have to find probability that p hat is greater than 10%. So because this is approximately normal, we have to find the z-score for 10%. So we're going to say 10% minus the mean, which is 0.08 over the standard deviation, which is 0.0172. This is going to equal 1.16563101, because our table only goes to 2 decimal places, so 1.17. We want to find probability that z is greater than 1.17. That's going to equal 1 minus phi of 1.17. And going to the table that I have, no, 0.77935. So this is going to equal 1 minus 0.77935. Perfect. Okay. And then that's the probability. What if I say this? A binomial experiment with 20 Bernoulli trials is being used to estimate the probability P of success in the Bernoulli experiment. If the actual value of P is a third, find the probability that the experiment will yield an estimate within 0.05 of the actual value and then 0.1 of the actual value. So I'm going to do this without the normal distribution just to show you how we would do it without. And then I think we'll go back and we'll do another example using the normal distribution. Okay. So because this sample is a bit smaller, it's a bit easier to explain how to do this as well. So we're doing some tests, we're doing some experiment. We have 20 trials, and we're trying to find the probability that the p hat that we get, we're trying to find the probability that the p hat we get is between 0.05 of the actual value. So if it's so what's the actual value? A third? So a third plus 0.05, and then a third minus a 0.05. That's what it's asking. What's the probability that the p hat that we obtain by doing the experiment and taking the number of x's and dividing it by n, what's the probability that that's a plus or minus 0.05 from that third? Okay. So let's let's actually go and try and calculate this. So how can one do this? If you say a third plus 0.05, what is that? Actually, we have to find out what these are. Third minus 0.05 equals 0.2833. Okay. Now, oh, and then of course, this P being a third is 0.333. So that's just something that we should note off to the side. Now, can we ever have P of being a third? Let's think about it. Remember, P is given by X over N. So that means X would have to equal P times N, which is a third times 20. Now, a binomial distribution is a discrete random variable. So 20 over 3 is not a discrete number. It's not an integer, is it? It's 6.66, whatever. Okay. So clearly we can't actually use this. Okay, like you would never get the 6.666. But that's not really the point. That's just sort of a little bit of a comment to make. So if this is going to be the case, let's find what these bounds would be in terms of X values. Okay. So again, we're just going to do whatever this P hat is times by 20 and times by 20. So we're going to convert this from being a proportion question to being a binomial question with just normal binomials and an X. Actually, I should multiply that by 20 as well. So the 5.67, and then the other one is 7.67. So the way we would calculate these sorts of proportions is by having X values of 5.67 and 7.67. So if I'm saying X has to be between these, well, what are the possible X values? It seems like this is just probability that X equals 6 plus probability that X equals 7, because those are going to give you sample proportions that lie between these two, which in turn lie between these two. Okay. And then how would you find this? Well, this is just normal binomials. You would say 20, choose 6. And then what was the probability? A third. So a third to the power of 6, 2/3 to the power of 14, and then plus 20, choose 7, a third to the power of 7, 2/3 to the power of 13. Okay. And then you evaluate what this is. So that's the idea. If you have questions where you're not going to be using the normal distribution, and you're not going to, because I sort of mentioned it here, then convert it from being a sample proportion question to being a normal binomial distribution question. It's a lot easier to solve that way. Okay, now have a go at the 0.1 of the actual value. It's a very similar process, and then I'll have a go as well. So pause, and then now unpause. So next part says between 0.1 of the actual value. So that means that you want your P hat to be between a third plus 0.1 and then a third minus 0.1. So this is the same as saying P hat is between, what's a third plus 0.1? 13 over 30. Oh yeah, do I really need a... No, I may as well, or else I know I'm going to mess up. And then 7 over 30. That's what it's effectively asking us. So let's convert this into x's. How many trials are we doing? 20. So multiply each of these by 20. 7 over 30 times 20 equals 14 over 3, which is 4.67. 13 over 30 times 20, which is 8.67. So now we would get simple proportions between 0.1 of the actual value if we had x values of 5, 6, 7, and 8. And each of these you can evaluate just using normal binomial distribution. So 20 choose 5, a third to the power of 5, 2/3 to the power of 15, plus 20 choose 6, third to the power of, yeah, we get the idea. Very nice, very nice. Now let's do a question where we have to use normal distribution. So consider this one. A survey of 2,000 Australian voters is being used to estimate the probability P that a random voter will vote for the Working Together Party. Assuming that the actual value of P is a third, use a normal approximation to the sample proportion distribution to find the probability that the experiment will yield an estimate within 0.01 of the actual value, and then within 0.02 of the actual value. So what you're saying is, for A, you want the probability that P hat is between a third plus 0.01 and then a third minus 0.01. Now, these are scores for the P hat distribution. Because we're going to be using a normal distribution, need to find the standardized Z scores. So for that, we need to find the expected value and the variance and the standard deviation of this the sample proportion distribution. Bruh. Anyway, skipping a few steps. The expected value of P hat is given by P, and the thingy is given as the square root of P, 1 minus P over N. Please don't reuse this. Okay? Like, I want you to actually prove it every single time, because I can just look back at a textbook if I really need to. You're the ones who have to know this in your exam. Okay? Anyway, the P is a third, and the standard deviation is what is this? A third times 2/3 over how many people? 2,000. Okay, so this is 0.010541. Okay, it goes on, but I feel like that's going to be more than necessary. Very nice. Now, we need to find the Z scores. So Z is a third plus 0.01. So I'm just going to write it like minus a third. Oh, yeah, this is good. 0.010541. And that's going to be 0.00100541. I think. No. No, wait, what am I doing? Oh yeah, that was some shocking maths on my part. Oh yeah, I did the thingy wrong. Not good. 0.010541. Oh, that was shocking. 7. Now, considering I can only go to 2 decimal places, 0.95. And then for the other one, it's a third minus 0.01. And then plus, and then minus a third over 0.010541. And this should just give you negative of that 0.5. Lovely. So what you're really asking yourself is the probability that Z is between 0.95 and minus 0.95, something of which is just going to correspond to that. Remember, these properties are very useful to know because it saves you a lot of time when you're evaluating this stuff. And this is two of those minus one. And going back to the statistical table, 0.95. 2 times 0.82894 minus 1. There we go. Very nice, right? Very nice. Yeah. And then the next one says within 0.02. So you do the exact same thing with the 0.02. Okay. Typically, I don't actually find questions like this in exams because I think these ones, like within this much of the actual value, it's not that interesting of a question. Better questions sort of come from this one website I've been getting questions from. Something like this. An economist wishes to investigate whether people are keeping cars longer now than in the past. He knows that 5 years ago, 38% of all passenger vehicles in operation were at least 10 years old. He commissions a study in which 325 automobiles randomly sampled. Of them, 132 are 10 years old or older. Find the sample proportion. And then find the probability that when a sample of 325 is chosen from a population which the true proportion is 0.38, sample proportion will be as large as the value you compute in part A. You may assume that the normal distribution applies, and then give an interpretation for your answer. Okay, so find the sample proportion. So let's see. It commissions a study in which 325 automobiles are randomly sampled. Of them, 132 are 10 years old or older. So the sample proportion is going to be 132 over 325. Nice. So this is 0.40615, but I think we'll just use the fraction version. Part B. Find the probability that when a sample of that much is drawn from the population, in which the true proportion is 0.38, so that means that's the P, the sample proportion will be as large as the value computed in part A. Will be as large as. So does it mean larger or more? Okay. So let's find the probability that p hat is greater than 0.40615, or rather the 132 over 325. So for this, we need z-scores and we need to find the mean and all of that stuff. So the expected value of p hat is just going to equal 0.38, and the variance of p hat is just going to be 0.38 times 0.62 over, what's the size? 325. Nice. And then I just square rooted it already just so I could find the p hat, and got 0.02692. So the z-score is going to equal 0.971. So we want the probability that z is greater than 0.97. This is going to equal 1 minus phi of 0.97. Okay, and let's go to 0.97. And it is 1 minus 0.83398. Okay, so that's this for part B. And part C says, given interpretation of the result in part B, is there strong evidence that people are keeping their cars longer than what the case was 5 years ago? Like, if you compare all of this and you say, well, 40%, and it was 38%, right? Because it says he knows 5 years ago it was 38%. So it means, can you really say that just because your sample proportion is 40% now, that people are holding onto their cars for longer than 5 years ago, just because it's 2% more, given that there's an 84% chance, or around 84, rather 83.4% chance that it's actually not higher than the 40%? No, it feels like you're more likely that it's probably the same or it's a bit less. Like, but it's definitely not. There's definitely not strong evidence to say that there's people are holding on to their cars longer. So we'll say no to that part. And I guess we can finish off. So this is the end of stats. Good job, good job. And there's not much else to not much more to go.